G'day. So far in Module 2, our focus has been on force and it being the driver of motion. We're now going to look at another key aspect of dynamics, which is kinetic energy, and looking at its connection to motion. So today we're going to be covering a lot of the basics that is required to understand dot point 2.2.3. So we're still doing Module 2 dynamics and focusing on the inquiry question, how can the motion of objects be explained and analysed? Now we've already looked at work and the change in gravitational potential energy as ways of analysing and looking at kinetic energy. We're going to be introducing a couple of extra little concepts, some of which have to do with the conservation of mechanical energy itself. So our learning intentions today is to understand the conservation of energy in mechanical scenarios. So when things are moving, how is energy being conserved? As well as be able to derive and use the kinetic energy formula, which connects kinetic energy to motion. So already we should be fairly familiar with the idea of the conservation of energy. Specifically, we're looking at the conservation of mechanical energy. What we say here is that, as always, energy is not created or destroyed, but is either transferred into another object or transformed into another energy type. A lot of the time when we're looking at physics and mechanics style problems, energy transfer means that one object with kinetic energy collides with another, and some or all of that kinetic energy is transferred from the first object to the second. An example of where kinetic energy can be transformed into another energy type would be in our examples of friction, where an object with kinetic energy transforms some of that moving kinetic mechanical energy into heat energy and maybe some sound energy as well. In class, we're going to have a look at the PhET simulation that I have got linked there, and that will help us sort of visualize this idea of, one, that energy is not being created or destroyed and that we can take into account all energy types in all places at all times, but then also look at how that energy can be transferred and transformed. So what we're going to be visualizing first in this simulation is the transformation of potential energy into kinetic energy. And we'll also observe how energy transformations differ when there is friction that's involved, leading to a lot of this energy being transferred into thermal energy. Now, while it's not explicitly in your syllabus, there is one key kinetic energy formula, and that is that K is equal to a half mv squared. And this formula can be another gateway like F equals ma is between dynamics and motion, that idea of a kinematic value like V being connected to a dynamics value like K, or EK, we sometimes write it as, for kinetic energy. So some things to note. K may also be represented as EK, which essentially just means kinetic energy. We measure kinetic energy in joules as well. Now I have highlighted here a second equation. You will notice that it contains the right side of the kinetic energy formula, the half mv squared. And here we're talking about sums of different kinetic energies, and that the sum of all of those kinetic energies at the beginning is the same as the sum of all of the kinetic energies afterwards. And that's quite closely linked to our idea of the conservation of energy. The kinetic energy at the beginning will be the same as the kinetic energy at the end. We know that there are some exceptions to the rule, especially when kinetic energy is being converted into, say, thermal energy through friction. But this is a concept that we're going to be looking at in a lot more detail when we look at section 2.3 of this module, which is all about collisions. For now, we're just going to be focusing on the basic equation of K is equal to a half mv squared. In the description of this video, as well as the slides for this module, I will also be including a link to a video from high school physics. As you can see here, there is a timestamp. I'm not getting you to watch the entire thing, but from this point here, what's being shown is a really good derivation of how we can actually get the kinetic energy formula. I strongly recommend that you have a look at that video, as it will help to round out your understanding of this equation and where it comes from. But our main focus for this video is going to be looking at how we can apply the energy formula in the context of a practice question. So in this question, we're being told that we have a 0.5 kilo box being pushed a distance of 45 centimeters with 18.1 newtons of force. However, as it moves, it experiences a kinetic friction force of 12 newtons what we need to do is calculate the final velocity of the box. What we're going to do first is record any relevant data that we have. So to begin with, I'm just going to draw a diagram and include anything that can be shown there. So we have a box, we have a push force of 18.1 newtons. We have a frictional force going in the opposite direction of 12 newtons. And to calculate F net, essentially we just need to do a vector addition here. So the net force here is 6.1 newtons. I'm also just going to draw an arrow to show the direction of that force, especially considering that I had to define all those directions. None of them were given at the beginning of the question. What I'm also going to record in this little data section here is the other information that we've been given that was not included in my diagram, and that is that the mass is equal to 0.50 kilos, and the S, our displacement, is 0.45 meters. Now, to answer this question, I'm going to need to use this new formula that we've been looking at, which is that EK is equal to a half mv squared. That will enable us to calculate the unknown final velocity. That's our unknown value. So we'll just have to do a little bit of work with the data that we have to calculate for the kinetic energy. Now, in order to do this, I'm going to have to look at our idea and concept of work in a little bit more detail. So a way that I can write about work is that the work done on the box is the change in kinetic energy on the box. And when we're looking at a change in anything, that's generally always just final minus initial. Now, in the scenario that we have been given, the initial kinetic energy is equal to 0. And what that means is that the work on the box in this example is simply equal to the final kinetic energy. What that means is, in the context of this question, we can say that the kinetic energy here that we have to substitute in, the final kinetic energy, is going to be equal to the work done on the box. And the formula that we have used previously for work done is the parallel force here, which will be the net force that was on the box, times the displacement. So in this case, the net force applied to the box as well as the displacement are both parallel to each other, so we don't have to do any trigonometry. We can just substitute those numbers straight in. So here that means work done on the box is equal to F net times S, which is equal to 6.1 times 0.45, which is 2.745 joules. And that, again, is our kinetic energy. From here, we can use the kinetic energy formula and solve for V. So to solve for V, I will multiply by 2 and divide by m. That gives us V squared is equal to 2 kinetic energy over m. Then square root both sides. Our V is equal to the square root of 2 times EK over m. Substituting those values in, and that is equal to 3.3 meters per second. Just an interesting side note, with the data that you've actually been given, you could also do this calculation without using the kinetic energy formula. This question can also be solved using F equals ma, and the kinetic equation V squared is equal to U squared plus 2as. Thank you very much, everyone. In the next video, we're going to be looking at the concept of mechanical power, which is quite closely related to this energy concept that we have brought in today. But until then, have a good one.